All right, our next speaker is Thomas, and he's going to tell us about efficient and near optimal noise generation for streaming differential types.
All right, thank you. So let me get started by just defining the problem that we're looking at, which is continual counting. So this is about coming out with a differentially private streaming algorithm. And wrong direction. And the key requirement is that we're interested in the space usage of these algorithms, and it should be sublinear in the number of iterations. So at each iteration, the algorithm is going to receive an input xi, and it's going to produce an output, which is going to be the sum of all the xi's it's seen so far, or it's going to be an approximation of that. The input can be a scalar or a vector. I'm not going to get too hung up about that. But then we're going to have some error metric. So we're just going to take the maximum variance of the answers. You could use a different error metric, but let's just stick with that. And in terms of what are neighboring inputs, basically we can change one of those updates by unit amount. Alternatively, you could just think about the L1 norm of the difference between the neighboring inputs. So the contribution of this work is to provide algorithms that are space efficient, specifically going to have polylogarithmic space usage. And the error is going to be near optimal. I'll give you some more details. But first, I want to take a little wee segue into the motivation for this work. And the motivation is applications to deep learning. So the standard algorithm for differentially private deep learning is dpsgd. Here's the equation. Hopefully you got some understanding of this from Pratisha's talk if you're not familiar with it. Here's what all the various terms mean. But we can take this recursion and write it like this. And now it starts to look a lot more like a continual counting problem. So basically, we're continually getting these updates. Each update is the clipped gradient, and we're trying to keep track of their sum. Now, dpsgd typically adds independent Gaussian noise at each step. Essentially, the observation is we don't need that noise to be independent. We just need that in aggregate is going to remain accurate. So we're allowed to add noise and let it cancel out over time. And roughly speaking, if you come up with better algorithms for continual counting, that does give you better machine learning algorithms. There are some caveats that I'm not going to get hung up on, but roughly this does work in practice. Okay, so let's go through our results and compare them to the prior work. So I'm going to suppress the privacy parameters epsilon delta. Everything we're doing is just Gaussian noise addition. So I'm going to talk about I'm going to sort of ignore the factor of like how much noise you'd add for a single counting query. Okay, so the most famous algorithm for continual counting is the binary tree mechanism. Originally, it was studied with pure DP, but you can easily just replace Laplace with Gaussian. And you get an error that is log base 2 of n. And it also has the right space, it's logarithmic. But there are actually better mechanisms than this. And if you dig through the literature, there is an algorithm that gets you a better leading constant. And this leading constant shows you that the binary tree is off by a factor of about 4.5. Now, I know that the theoretical computer scientists don't care about constants, but in the applications, this does matter. Now, there is a very nice explicit construction, which is close to the non-constructive upper bound. And this is a very recent work by Fichtenberger, Hensinger, and Jalaj Upadhyay, who is there. And that's going to be the basis for our work. The problem with this is that there's no obvious way to turn this into a streaming algorithm. You'd have to have linear space, keep track of the entire input. Now, there's also lower bounds here. So if you're doing Gaussian noise addition, there is a lower bound that shows that the leading constant is tight. Now, if you move away from Gaussian noise addition, we don't have tight constants. This lower bound is what the previous talk by Xin Yu was about. But the practical algorithms are Gaussian noise addition, so that's what we're going to stick to. Okay, So let me tell you about our results. So our main result is that we get an algorithm that has the right leading constant, so a natural log of n divided by pi, and essentially a very small loss in the additive constant. And the space is log squared n, which is slightly worse than log n, but not too bad. So we also have a result that gets you arbitrarily close to the right leading constant and also has logarithmic space. So we're kind of getting the best of both worlds. We're getting the right constants and we're getting good streaming algorithms. Okay, so now I can show you what these numbers actually look like in practice. So the binary tree mechanism is the line that just goes off very rapidly. So you can see that there's a significant difference. And then the dotted and dashed lines are the various upper and lower bounds that are out there. And then our algorithm, so the FHU factorization, the previous algorithm I told you about, is the orange line. And then our algorithm is the solid blue and solid green lines that are very close to that. So we're slightly worse than these than this prior work, but in exchange we get polylogarithmic space. Okay, so I've told you what the results are. Let me now very quickly go into what's going on. So the key thing is that we have to view this as a matrix factorization problem. So I told you this is the task of the algorithm. It's supposed to output the prefix sum. We can view this as multiplying by some matrix A, where A is all ones below the diagonal and zeros above. Now we're interested in Gaussian noise addition. So we're adding Gaussian noise with some covariance sigma. And an equivalent way to do this would be to look at the Cholesky decomposition of that covariance matrix and then sample independent noise and multiply that by B, which is the square root. Now, matrix algebra is fun. There's different equivalent ways of expressing this. In terms of privacy, it's fairly easy to see that by post-processing, this is equivalent to just making sure that C times X plus independent noise is private. So now we just have to analyze the norm of the sensitivity of C times X, which boils down to the maximum column norm of C. So the amount of noise we add is going to be the maximum column norm of C times something depending on your privacy parameters. On the utility front, our error metric ends up just giving you the maximum row norm of B times the scale of the independent noise. So overall, our error is going to scale with the maximum row norm of B times the maximum column norm of C and our privacy parameters. So basically, we boil it down to this optimization problem. We're trying to minimize the maximum row norm of B times the maximum column norm of C, subject to the constraint that B times C is equal to this A matrix that gives us the prefix sums. Okay, so that's the general view. Let me just bring back to the streaming setting. So in the streaming setting, we're trying to do this computation. We're doing it online. And basically, we need to be able to do this on the fly. We can sample the independent noise as we like. And then the question is, how do we compute this? And now the reason we're really interested in space efficiency is that for the machine learning applications, we're talking about millions of iterations, billions of parameters. So just storing the entire input or the entire output or the entire noise that you've generated is infeasible. Now, I've written up the optimization problem. We're going to have to add some additional constraints to those factors B and C to ensure that we can do this efficiently in the streaming setting. Now, the binary tree mechanism, basically what it does is it comes up with a factorization that is sparse. So if you write it out, the matrices they're mostly zeros with a couple of ones. and that is what makes them efficient. We're going to come up with a different structure than that. Okay, so let me tell you what the FHU factorization is. So this is basically it. It's a matrix, which is a nice structure. So the diagonals are all constant. So this is what's called the Toeplitz matrix. And the values on those diagonals are described by this very simple recurrence. And if you want to know where this comes from, basically it's the Taylor series of 1 over square root 1 minus x. And we call this the generating function. And what's interesting, and this is a result that we show, is that this factorization is the exact optimal factorization if you restrict yourself to these Toeplitz matrices with these constant diagonals. Okay, so that's the starting point for our work. The overview, basically the way we're going to address this, is to come up with an approximation of the FHU factorization, which is still Toeplitz, still lower triangular Toeplitz. And we're going to add some additional constraint to make sure that we can do efficient computation. And our algorithm, which we call the BLT algorithm for buffered linear Toeplitz, is space efficient if the sequence of diagonal values is represented by linear recurrence. So here's a linear recurrence illustrated here. So you've got a bunch of coefficients, Q1 through QD, and the kth value can always be expressed as some linear combination of the previous D values. As you can see, the FHU factors do not satisfy this because there's a recurrence, but it depends on the index K. Now, having a linear recurrence representation like this is equivalent to the generating function being rational. So a ratio of polynomials. As you can see, the generating function corresponding to the FHU factorization is not rational. It's got a square root in it. And there's other equivalent requirements, such as being able to express the coefficients as some power of a matrix times some vectors. Now, I'm not going to go into the details, but the intuition is if you have this linear recurrence, that tells you that if you have the previous D outputs plus the next input, you can compute the next output. So that basically gives rise to our algorithm. Now, in terms of actually like parameterizing this, coming up with instantiating this, the theoretical approach that gives us this log squared asymptotic says we come up with a rational function that uniformly approximates the FHU generating function. So it's a rational function that approximates 1 over square root x. In practice, we could just directly optimize this to get even better results. But that's roughly the overview of how we prove this result. So let me wrap up. Again, our contribution is to come up with a streaming DP algorithm that simultaneously is getting close to the optimal error and only has polylogarithmic space. So binary tree would have suboptimal error, but the right space, and prior methods that give you the right error would have linear space. And I know I'm going to lose my theorist card for saying this, but constants do matter. And in particular, this is quite relevant in the ML applications. We are using this stuff at Google. There's a couple of directions for further work. So I told you we have 2 results. One that gets the right leading constant, but has log squared n space. One that like slightly loses on the leading constant in exchange for getting a log n space. Can you get them both at the same time? there's also the question of studying other matrices other than this all ones matrix. Fairly natural. And then there are other objectives that you might want to look at. So I looked at the maximum variance. You could look at the average. You could look at different sensitivities, sort of different neighboring inputs. And you could also switch the expectation and the maximum. So then you'd have to like see if you can see if you can bypass the union bound. And that's it. Thank you.
Thank you. So I want to follow up on the last item. So for ML applications, which error metric is the most useful?
That's a very, very good question. And we don't have a good answer to that one. Like we don't, we know that obviously lower error is better, but whether it's the maximum, the average, or some kind of weighted average, we really don't know.
Sorry.
Can't answer that one. You won't be able to answer this one either, but I just wanted to ask it. There'd be an expectation that there would be different objectives that would be better for different ML applications, especially dependent on the distribution properties for the data type.
Yeah. So, okay, I can maybe answer a little bit more detail. So we do have some work that studies like very restricted examples like quadratic loss functions. We can kind of derive what the right objective function is for that in some like weird asymptotic sense. So there is some way to like try to get at this, but ultimately these machine learning settings are kind of a black box. We don't really understand how they work.
Okay, I think we have to move on to our break.